Mr. Ryan, are you right? Yeah. On day 28, okay? On day 28, we talk about how to check if a binary search tree is valid. Yeah. What's binary search tree?
Is a tree. Is a tree that the left is smaller than the parent and the right is bigger than the greater than the parent.
Okay.
Strictly.
Is this a...
No,
Why is that?
because -1 isn't greater than
Yeah,
1.
that's right. So binary search tree, obviously at the beginning it should be a binary tree. Binary tree is that each node has at most 2 kids, right? This is the rule. The nodes with no children are called leaf. There's only one node which doesn't have any parent, we call it root. For each node it has at most 2 kids. That's binary tree. And binary search tree has this additional criteria, like the nodes on the left trees are strictly smaller than the parent. The nodes on the right tree are strictly bigger, right? So look, this -1 is smaller than 2, but it should be bigger than 1. So this is not a binary search tree. But if I put these here, 1.5, is this a binary search tree?
Yeah.
Yes, this is a perfect binary search tree. So on day 28, so we want to check if a binary tree is a binary search tree. At that point, we talked about the recursion algorithm. So basically, we have maintained a window, so minimum value and maximum value. Yeah, maximum value. So we maintain this window for the node value. So one look at the beginning, we don't know the window, so we set it to -infinity and +infinity, right? As soon as we travel to the left or travel to the right. If we travel to the left, look, this window, yeah, left and right. It should be bigger than the left and smaller than the right. So if we travel to the left, what happened? Look, the range of the value for the current node is from infinity, -infinity to +infinity. This one is at this range. If I go to the left, what happened to the window?
It goes smaller.
Smaller, yeah. Look at this one. So the window becomes -infinity to 1. If we go to the right, what happened? The number should be bigger than 1 and smaller than infinity, right? So every time we travel to the left, we update the window and accordingly. If we travel to the right, we update the window accordingly. And at each node, we just check if the value is inside the window, all right? Okay, so can we have these duplicate values in a binary search tree?
No.
Why is that?
Because if there's duplicates, it wouldn't be strictly smaller.
Exactly, yes. Because we're talking about strictly smaller and strictly bigger. If there are duplicates, then certainly doesn't mean this requirement. Okay. This is a very straightforward recursion algorithm. We just keep tracking of the window, and then if we move to the left, we update the window. If we move to the right, we update the window, and then we validate the binary tree to see if each node is within their windows. Okay, let's do this. Define f at the beginning root the window minimum value and the maximum value. Right? At the beginning, we can set this min value, maximum value by default -infinity to +infinity. Okay. If there is no root and validate, we just return true. Right? So now, look, if this value, if root of value is smaller than mean value, right? Or the root of value is bigger than the max value, then what should we do? Return true or false? Current window is mean to max, not equal, right? Because as we said, we don't have duplicate values, so it's just strictly bigger than mean, smaller than max. So if this value turns out to be at somewhere here or somewhere here, then we should return true or false. If it's not in the window, we should return true or false.
False.
False. Perfect. We just have to check the left tree. The left tree has to be a binary search tree, and the right tree has to be a binary search tree, right? In order for the whole tree to be a binary search tree, right? Look, if this is a 1 and then this is the left tree, this is the right tree. Okay, so we want to check if this binary tree is a binary search tree, right? So now I'm telling you this one is within the range. So we have to check if this bit. Yeah, this bit is a binary search tree, and this bit is a binary search tree, right? This is a subproblem, recursive subproblem. So look, we have to check f root of left. This is the left tree, and then the window thing. We go to the left. The left boundary does not change. So this is mean v. What's the right? What should we do with the maximum? If we go to the left, what's the maximum? Going to be this window. The node here, what's the maximum? If we go to the left, what's the maximum of this node?
The top.
1, right? Root of value, yeah? But not equal to, right? And, okay, now we check the right. So if we go to the right, what happened to the mean value? What happened to the mean value? If we go to the right, what happened?
The mean.
What's here? What's here? If we go to the right, what's the mean? Root of value, yeah? And what's the right boundary does not change, yeah? If we go to the right boundary does not change, okay? So look at this is recursion. Time complexity On, we travel every node. The space complexity On, yeah, because we're using recursion, yeah. Technically, more precisely, the space complexity is OH, okay? H is the height of the binary tree. In the worst case, H equals the number of nodes. Okay. And we can turn these, on the day 28, we just talk about recursion, but we don't talk about how do we turn this into iterative. We can use the iterative, right? The point is that when we maintain the stack ourselves, for the recursion, we ask the computer to maintain the stack, right? So the recursion, calling itself, right? That's computer calling itself. This maintains the stack for us. So we can maintain the stack ourselves, but for the elements in the stack, every time we need to push the root, the current node, and the left value and the right value, the window, right? So then we can validate the values. Stack, yeah? Stack at the beginning, we put it to the root, and then at the beginning, the window is minimal infinity to positive infinity. Right? This is the tuple. Tuple contains 3 elements. What's tuple? What's the difference between tuple and a list?
Immutable.
Tuple can't change.
Tuple can't change.
This
Right?
can.
This can. Yeah. Tuple is immutable. Immutable can't change. Right? So for example, A equals 1, 2, 3. I can't say A0. I want to change it to 6. I can't do that. This is because it's immutable. But if I say A equals list, this is the list 1, 2, 3. If I say A0 equals 6, then what happened? A will become 6, 2, 3. Okay? We change it. Right? This is a tuple, immutable. This is the list, immutable. Okay? At the beginning, we push this root element. Okay? If not root, we better to check. If not root, return true. Okay? We push the root. The minimum infinity to positive infinity. The window is huge, right? Infinity at the beginning. Now we check wire st. Then we get the root. Root the lower the right equals st dot pop. And we check if root of value. If root of value is smaller than r or smaller or equal, or root of value is bigger than equal than r, then we return false. And then return false. Then if root of left, if we have a left kit, then we push append what? Append root of left. We go to the left, we update the boundary. The left is still the same, which is the air. The right boundary is root of value. Right? And then the same goes to the root of right. If we have a root of right, we st dot append root of right. The left boundary becomes the root of value. The right boundary stays unchanged. And if we finish this iterative search, then we return true. On the right, this is just the iterative version of the left, which is the recursion. This is one way. Another way about binary search tree. So look, what's so important about binary search tree? What's good thing about binary? So why are we organizing the data in such a way, like the left are smaller, the right are bigger? What advantage can you get?
Because for other problems, binary search tree might be more easier to do than vanilla binary.
Okay, so we are separating the data. So binary search tree. So if we want to look for a value in the binary search tree, then that will give us advantage by using the binary search tree, right?
Yeah,
because like if we want to look at this, if we want to look for 1.5, is it bigger than 1? Then it's definitely on the right, right? It's not on the left. If the left has lots of the data, we can just ignore that, right? Because it's not there. It's bigger than that, it's on the right tree. If it's smaller than 2, it's on the left tree, right? Right? If this binary search tree is highly balanced, right? Highly balanced means that the maximum difference between the depth of the left tree and the right tree are no more than 1. Then it's highly balanced. Highly balanced if the n nodes, on average, the height equals the log n, right? So log n. So if we want to look for a number in a tree with n numbers, then we just need log n, right? This is a major improvement than the linear search, right? So if there are a million numbers, unsorted, a million numbers, in the worst case, if you are really, really unlucky, if you want to find a number in a million numbers, how many times can you try in the worst case? Yeah, you try from the first one, second one, third one until the end, right? It's linear, right? But if this number is sorted, right? Remember we talked about binary search here. The same thing goes here, right? Binary search if the numbers are sorted, right? 1 to 100. Remember the guessing game. I have a number in my mind. Can you guess?
50.
50.
50.
Yeah, you guess always in the 50. I say okay, the number you guess is bigger.
75.
Is bigger than
25.
Yeah, you go for the lower half. Okay. So always cut in half, right? So this speeds up. So log n. Okay. Okay. So coming back to this binary search tree, in what order? If we travel the binary search tree, in what kind of order? That gives an order list. Okay. So we perform which order on a binary search tree, then gives us the order sequence.
In order.
In order, yeah. In order. Left. We visit the left tree, root, and right tree, right? If we perform this in order thing, then we can check if the root value, if this value is bigger than the previous one, right? If it's smaller than the previous value, then it's not true, right? So okay, let's quickly write this. Do you understand this? If we travel the binary search tree in order, and we always remember the last value, right? And the last value should not be bigger or equal than the current value, right? So the previous one equals at the beginning minus infinity, right? This is the lower bound. Define depth search or in order. Root, right? If not root, return true. This is the same. Okay. Now look, if root of value, if this value is smaller or equal than previous, if it's smaller than previous, then we return true or false. This 1, 0, 2. So this is the current root value. Previous value is this one. If this value is smaller or equal than this one, what happened? If this value is smaller or equal than the previous value, so what happened? Previous value in order, what happened? Return true or false. If this value is smaller than the previous value in order, so what? False. Return false. We just have to update previous equals root of value, and then we just return. We just keep checking. We just keep checking the right tree. So which is depth search root of right. Okay. Okay. To sum up, this is in-order traversal. Because we perform an in-order traversal on a binary search tree, then we give it in order. So when we do this in order, we use previous to remember the last value. So remember the last value in before this current value, right? So if this root of value is smaller or equal, if it's smaller than the previous one, then obviously this is not sorted after the in order, then it's not a binary search tree. Right? The same time complexity, O(n) time, O(n) space. We can also turn this into the iterative. Okay, iterative. I'm going to quickly write this iterative, and that will be. And just think about what have you learned today. Okay, for the last question, everyone. St equals at the beginning empty. The previous equals minus infinity. While st or root. While root, we keep pushing the left. St dot append root. Root equals root dot left. So the idea of this iterative is we keep going to the left as deep as we want, and we push the key to the stack, right? And then now we get it out. Root equals st dot pop. Then we compare. If root of value is smaller or equal than the previous one, then we return false. Right? Otherwise, we remember the previous one equals root of value, and then we go to the right. Root equals root of right, right? This is the standard approach of turning this in order from the recursions to to the iterative, and at the end we return true. Okay. Okay, the same time complexity and space complexity. What have you learned today? Come on, the last question.
About validant.
What's new today? So on day 28, we talk about recursive algorithm to validate the binary search tree.
Using other algorithm to
Algorithm.
validate.
So the first algorithm we talk about is the window. Yeah, window thing. We go to the left, we narrow the window. We go to the right, we narrow the window. So we just check each node to see if it falls in the window. This can be done in recursion and iterative. Today, what's this? What are we doing here?
In order.
Yeah. So what do we do with it?
Put it use in order.
Yeah, we use the in order traverser to travel the binary search tree, and then we just have to validate the binary search tree, validate the node to see if it's strictly bigger than the previous node in a sequence. Because that's based on the fact that if we perform an in order traverser on the binary search tree, we get an order sequence, right? So we have to check if it's smaller or equal than the previous node, then it's not a binary search tree. And obviously we can do this in recursion and iterative. Okay, that's it for today. Bye bye. Bye bye.